In the previous discussion, we saw how to calculate centers of mass even if the mass density is not a constant. In this short video, I'd like to look at a specific example of that. We're going to look at the region in the first quadrant that goes from x equals 0 to x equal 2, and also y equals 0 to y equal 2. If the mass density was uniform, you would expect that the center of mass would be at the center of the square at x equal 1, y equal 1. But because I'm going to use a mass density that is 6 times x plus 2 times y, it's likely that that's not going to be the case. The first thing we have to do is to find the mass. The limits of integration 0 to 2 on the x refer to the smallest and biggest x values. The 0 to 2 on the y integral refers to the constant functions that determine the top and bottom of the region. When doing the inside integral, as always, y will be the variable, and we will treat the x as though it were a constant. The inside integral, as expected, is a function of x, 12x plus 4 here. It's this function that I have to integrate from 0 to 2 with respect to x in order to get the mass. The mass works out to be 32 units. Since the inside integral is being done with respect to y, I can pretend that the x is a constant and factor that out of the inside integral. This leaves the same inside integral that we did when we got the mass, so I may as well reuse the result. Converting it into the usual calculus 1 integral, and then doing the usual procedure, we find out that the moment about the y-axis is 40. Unfortunately, in the double integral for the moment about the x-axis, in the inside integral I have a factor of y, which is the variable of integration, so I can't pull the y out and reuse anything. We'll have to calculate the new inside integral as is. The quantity that I have to integrate with respect to x in order to get the moment about the x-axis then is 12 times x plus 16 over 3. Carrying out the resulting integral with respect to x, we find out that the moment about the x-axis is 34 2/3 units. We now know everything we need to know in order to calculate the center of mass. As previously mentioned, if the mass density were uniform, you would expect the center of mass to be located at x bar equal 1, y bar equal to 1. Here we see that x bar and y bar are somewhat bigger than 1, with x bar being the one with the larger difference. This is to be expected. In the mass density, the coefficient in the x term is larger than the coefficient in the y term, so we expect the center of mass to be shifted to the right and upwards, with the shift to the right being more noticeable. This has just been a quick calculation of the type that we've been talking about. This ends our inappropriate language section. In the next video, I'm going to show that this more sophisticated idea reduces down into the formulas that you'll find in the textbook if you have uniform mass density. I hope everyone has a good day. I'll talk to you again soon.